Okay, so we're gonna be using vectors a bit more now. We used them previously for geometry problems, and now we're going to start to see how they can be used for mechanics or physics style questions. There'll be a lot of use of vectors when you start doing more mechanics style stuff, but for this chapter it's just called modeling with vectors. So it's not going to be too mechanics heavy, but we are going to talk about some more physics-based terms. So you can see a few there on the screen: velocity, force, speed, displacement, distance, acceleration. I should throw that one as well on there actually. In fact, I will. So first question that I just want to ask, and I'll reveal all in the next slide. Given that vector quantities have magnitude and direction, and scalar quantities are just numbers, no direction, which of the following words do you think apply to vectors, and which do you think to scalars? So just mentally add either a V or an S next to each of these words. Which one's vector, which one's scalar? Have a think. So which ones of these have directions? So velocity is vector, force is a vector, displacement is a vector, and acceleration is a vector. Speed is a scalar, and distance is a scalar. Just double check I've done that correctly. Yeah. So you may have encountered this before, but if not, that's the correct answer. And for an easier way to remember it, let's now look at the sort of logical arrangement of all of these terms, so we can kind of see why it makes sense to have so many words for what seem like the same thing. So I'm gonna just draw up a table. I can't do straight lines very easily with this, but I'll give it a go. Not too bad. And what we're going to do is effectively have some quantity, and there's going to be two versions of it. There's going to be the scalar version, and there's going to be the vector version, and then we can just clear up how we refer to each of these. So the first quantity I'm going to talk about, I'm going to use non-physics, non-mathematical terms. I'm just going to write the words how far, and then we'll say how fast. It's a bit hard to do the third one. Let's go there in a moment. So first of all, how far as a scalar, this is distance, and as a vector, this is displacement. Okay, so an example of that would be, I don't know, someone says, how far are you from school right now? And I could either say I'm a mile away, or a kilometre away would probably be better. That's a distance. Whereas if I said I'm a kilometre away in the northeast, now it's not a most direct way of giving a vector, but that is a vector because I've specified the direction. If you know I'm a kilometre away from school, I could be anywhere on that circle. That's 1 kilometre around the school. Whereas if I say which direction, you know, no one would ever say this, but let's say I'm a kilometre away from school at a bearing of 20 degrees, right? That's a displacement in some sense. Or perhaps a more realistic example could be, let's see, if I've got, let's say in one dimension, if someone says, you know, how far are you from the Earth's surface, right? Or let's say, how far are you from the surface of the ocean? If you say 2 meters, that could either be 2 meters above the surface of the ocean or 2 meters below. So this is in one dimension, right? Whereas I could, as a vector, I would say either plus 2 meters being above sea level, or maybe minus 2 meters being below sea level. So that's a one-dimensional vector in some sense, where we use plus and minus to distinguish the direction. Okay, so distance is always a positive number, single number, whereas displacement, if it's one-dimensional, it'll be a positive or negative number. If it's two-dimensional, it'll be a vector, and we'll usually use a column vector or IJ notation. Okay. For how fast, scalar is speed, and vector is velocity. And the stuff I said for the previous row still applies. Speed is always a positive number, and it's simply a number without a direction, whereas velocity is how fast are you going and which way are you going, and we usually express that using a vector. And then finally, the last one, I mean, this is effectively acceleration. Let's assume I'm allowed to reuse a word from before. How fast is your speed / velocity changing? Okay. How fast is all that changing? So here is the case where we don't actually have two distinct words. As a vector, we call it acceleration. Acceleration is a vector. And for scalar, we don't actually have a special word. So we'll just, and you'll sometimes see it written as this, magnitude of acceleration. Okay. In layman's terms, and in terms of how people just talk to each other, we tend to use acceleration as a scalar in real life. If you say, "Oh, my car's accelerating at, I don't know, 5 meters per second," that would be a magnitude. It's not a vector. You haven't said which way it's going, but within mechanics and within physics, acceleration is actually a vector. And if you're just giving the number, then it would be magnitude. I'm conscious I've probably spelt acceleration wrong. Okay, Google tells me I haven't. That's fine. Cool. So that's it. Those are the terms. The only one we've missed off is force. Let's just put it here quickly. We've got force, and again, it's just a vector by default. And if we wanted to talk about it as a scalar, we would say magnitude of force. Okay, we don't have two different words for it. We just use it by vector as default. Cool. So hopefully that makes sense. Now let's start using some of these things. So before we start using some of these things, actually, we just want to further define something to do with cardinal directions. So you've got these cardinal directions, which is north, east, south, west, and everything in between. You'll see in some of the questions coming up that certain vectors and directions are just disguised as cardinal directions. So it's good for us to be able to interpret those correctly. So for instance, if I said, and I think I did this as an example in a previous lesson, let's say 3 kilometers east and 5 kilometers north. As a vector, that's 3i and 5j. Okay, assuming my vector is in units of kilometers. So to just clarify then, what you've effectively got is that you can interpret north, east, south and west as the following. North is just going to be, sorry, let's do east first. East is going to be I, north is going to be j, south is going to be minus j, sorry, let me rub that out, minus j, and then west is going to be minus I, okay, multiplied by however far it is. So if I was southwest, for instance, then I'd have equal quantities of minus I and minus j, right? So that's just how you interpret cardinal directions. Shouldn't be too confusing. So let's take a look at our first example. A girl walks 2 kilometers east from a fixed point called O, makes sense, origin, to a point A, and then 3 kilometers due south from A to B. Find the total distance traveled. So quick diagram here. We've got O, we've got A, then south is B went 2 to the right and then 3 down or south. Now, total distance travelled is there. You could technically do this without vectors, but we can just use the principles of vectors to answer this for us. So to do it formally, we're going to say, because we want to get used to using the formal terminology, her displacement, right, which is how far as a vector, is equal to 2 minus 3. That's her displacement. And then the distance, which is the magnitude of displacement, the scalar form, is this. And that is 2 squared plus minus 3 squared, or just 3 squared. And we get the square root of 13. Let's come up again. Okay. You could just use Pythagoras, but what you'd effectively be doing is answering it in what is effectively the vector form of answering the question. Okay, and we're going to do it this way for this case because we want to get used to using these words, displacement and distance and so on, and using the notation correctly. So then let's look at part B. The position vector of B relative to O. Okay, that's useful because we've done that. It's 2 minus 3. That's what B is. That's the B position vector. So let's actually be specific. That is OB is 2 minus 3. Okay, it's getting us to repeat ourselves a bit, it seems. I think this is partly because we did it properly for A, and because we did it so well, now it's just kind of repeating it a little bit. So magnitude of OB, we just saw, that's root 13. And then D, the bearing of B from O. I've never been a fan of bearings myself because they're not really a mathematical concept. They're more of a, I don't know, a navy concept or a navigational concept, but they've survived into A level. So bearings are always taken from north. So we want this angle. I want the green angle, but I'm going to work that out by saying that's 90 degrees. And this is theta. So it's going to be 90 plus, and then to get theta, it's going to be tan inverse of opposite over adjacent, which is tan inverse of 3 over 2. Okay, and you'd put that in your calculator, and that will give you your answer. I don't have it in front of me. So tan inverse 3 over 2 plus 90, and you've got your answer. Okay, simple example. Okay, so then final example. Let's take a look at this one. In an orienteering exercise, a cadet leaves the starting point O, 15 kilometers on a bearing of 120 degrees to reach A. I think we're going to have to draw a diagram, aren't we? So we've got O, a bearing of 120 degrees. So that's 90 plus 30. So it's going sort of this way. And let's label our angle. So that's 30 degrees. And walks 15 kilometers. So that's 15 to get to A, the first checkpoint. And then from A, they walk 9 kilometers on a bearing of 240 degrees. Okay, so that's 90, 90, 180, 60 degrees. It's roughly there. Okay, I'm obscuring a bit of the working out here, but hopefully you can see why that would be 60 to get a bearing of 240. And that's 9 kilometers to the second checkpoint, and there's B. Let me just make that line a bit shorter. Okay, there's B. And then from B returns directly to O. Okay, so then goes there. Find the following, the position vector of A relative to O. Okay, first of all, I just want to draw this diagram a bit bigger. Hang on. Okay, so we've got the bigger diagram, and then we're going to find the position vector of A relative to O. So O is here. Okay, so we know the position vector of A is going to be a positive number horizontal, or the I component, and then a negative value down. We just need to find what that is. In fact, we can quite easily do that by connecting up these dashed lines, and these are just construction lines. That's 90 degrees. We've got the 30 degrees here. We've got a hypotenuse, so we can quite easily work out this adjacent and the opposite. That adjacent here is going to be 15 cos 30, and this opposite here is going to be 15 sine 30. We should know off by heart really. Sine 30 is a half, cos 30 is root 3 over 2. So I'm going to get here as my answer 15 over 2 root 3, and then 15 times a half is just 15 over 2, but it's negative, right? This is a negative component because we went to the right by 15 over 2 root 3, and then we went down minus 15 over 2, and that gave me OA. So this is my OA position vector. Right? The OA vector is the position vector of A. Cool. You might be asked to find the values of these. I'm just checking the book. It gives this one a value of 13.0, but hopefully you can confirm that. So then we want to find the magnitude of OB. So this is why actually it's quite good to keep it in third form. I'm going to just do that down here. Oh, sorry, that's OB, not OA. Right, magnitude of OB. Let's have a look at that. So I think probably the easiest way to do this is to use your knowledge of geometry. So this is actually a bit of geometry again. So we want OB, that's this side, right? Now we already have two of the sides. They're 15 and 9. And we've effectively got angles as well. If I just fill out this diagram a bit more, that angle there, that must be 60, right? Because we've got 30 here, 90 there. So 60 makes that 180. And then because we're on a line, a vertical line, making 180, this here must also be 60. So now we've got one of the internal angles of the triangle here, 60, and we've got two of the adjacent sides, 15 and 9. And I want this opposite side. So we can actually just use cosine rule to answer B, which is going to be, well, the magnitude of OB squared is going to be equal to 15 squared plus 9 squared minus 2 times 15 times 9 times cos 60. Okay, we just make use of cosine rule. And I haven't got the calculator, but that works out to be 171. Yeah, so then magnitude of OB root 171. Okay. Right, the bearing of B from O. So this is a good thing we drew the diagram, right? Because this would be very hard to do without one. What's the bearing of B from O? This is partly testing us on our knowledge of angles, I suppose, or perhaps the sine rule. I think we'll go with sine rule for this one. So to get the bearing, I effectively want, well, that's 90 degrees. And then that bit there is 30. So now I just need this bit. I'm going to call that theta. So the answer will be 90 plus 30 plus theta. How do I get theta? Let's use the sine rule. Because sine of theta divided by the side opposite, which is 9, must be equal to sine of 60, which is that angle, divided by the opposite side length, which is this one here. And we just worked that one out. It was root 171. So therefore theta must be equal to 9 times sine of 60 divided by root 171, and then we're going to want to take the sine inverse of that. Okay, so I'm just rearranging that equation. So we get our theta. So we do 9 times sine 60 over root 171, take sine inverse, and then we still need to just add on 30 and add on 90. And that should give us our final answer. So C is theta, whatever that turns out to be, plus 90 plus 30, so plus 120. And that should give us 157. Maybe double check on your calculator. You can always get a house point if it's wrong. So that should give 157 degrees. Cool. And then finally, the position vector of B relative to O. Okay, the position vector of B relative to O. So I'm going to clear up some space first. So if I want the position vector of B relative to O, what I effectively need is this green stuff. I need that height there. That'll give me the J component, and I take the negative. And this horizontal distance here, right? This is 90 degrees. Do I know any other angles? Okay, so that theta, I should actually write in what that is. We calculated it below. It was sine inverse 9 sine 60 over root 171. What does that actually come out to? So it's actually about 36.6. Is that theta? So if that's 36.6, then this angle here, if you think about it, this is 30 plus 36.6 is going to give me that angle added on will then give me 90 total. So 90, all right, I'll just get the calculator. 90 minus 30 minus 36.6 is about 23.4. And then I suppose we could also just fill this one in just for good measure. So that will be 90 minus 23.4 gives me 66.6. Okay, and then remember the length of this thing is root 171. So now you've got free choice. You can either use the 23.4 angle or the 66.6 angle. I think textbook's gone with 66.6, although they rounded it to 67, which I think is a bad idea. You shouldn't round it in the middle of your calculation, at least not that much. You should try and keep as many decimal places, 2 or 3 if you can. But in terms of the principle of how we do this, we're going to do root 171 times cos of 66.6 and root 171 times sine of 66.6, and that will give us our answer. So that distance there is going to be, so that's opposite, so that's root 171 sine of 66.6, and then this green horizontal length there is going to be root 171 cos of 66.6. And then, of course, because it's going from O to B, that first one will be negative because it's going down, but this one over here will be positive because it's going to the right. And that will be your final answer. So for D, it's just one big vector where it's these values, and then of course you'd put those in your calculator and you'd get a specific number, and then you just have a simple column vector with 2 numbers in it. Okay, I'd work those out. I'm not going to do it now because time allowing, but yeah, that's it. That's how you'd find the answer. Cool. All right, so time to try some questions yourselves. So there's 4 questions in total, 2 on this page, one on the next page, and then one on the third page. See how you do. Try these two first. You can pause the video now. Okay, and there's our third question. See how you do with that. You're going to have to, I think, for 7C, look up your, it's another kind of sign rule for area, most likely. And finally, you've got our fourth question. See how you do on this one.